There are zillions of really sad design stories in which new concept is great, prototype flies, and the performance seems to be much superior to the competitor's one. So design team guys already put sparkling on ice, but the product never makes it to the market, or miserably fails shortly after mass production begins. Why? Because the product turned out to be too hard or too expensive to manufacture. That is why we have to keep in mind manufacturing and assembly during our design phase. And that is why in our course of artificial inventiveness, we have this short introduction to specific design instrument called Dfma, Design for Manufacturing and Assembly. First stories of smart redesign of goods to make them cheap to manufacture dated back in 19th century, so the idea is not new at all. Henry Ford described his efforts to design a car that is not just functional, but easy to manufacture and assemble in thousands. General Electric Company is known for value engineering approach that definitely hits the same target. In the middle of last century, mechanical design and metal manufacturing, metal sheet manufacturing, became the home court of Dfma. And very soon the approach made it to general manufacturability or productivity methods theories. It has become a part of DFX, a collection of design tools to address specific targets. Design for function, design for cost, design for reliability, variability, recycling, and so on. We will see soon that Dfma has strong links with other concepts of systematic design. And again, ideal final result from trees seems to be the champion and holds the general idea. Ideally, the product assembles itself, right? Dfma is often associated with lean because it's all about identification, quantification, and elimination of wastes or inefficiencies in product manufacturing. I'm sure you can speak some Japanese like Pokayoki, Muda, or Kanban. I would only notice that lean principles are mostly meant for non-engineering part of design world, mostly managers. These principles are softer, more common sense based, more strategic. I am sure that nothing can beat a good example to tell what is the main idea of Dfma. Here are three fighters of World War II time. And please, you don't need to be an aerodynamic expert. Let us just check our intuition. But what do you think? Which plane could fly better? More maneuverable, powerful, higher speed? Yeah, it was number 3, legendary British Spitfire. Excellent aerodynamics, performance due to elegant curves of the body. Now, what do you think? Which one was easy to manufacture, to produce, to assemble? Right, that was number 1, German Messerschmitt 109. Straight line, square elements, flat glass on the cockpit, and the cannon that could now fire through the hollow propeller. It made it the classic of Dfma. The consequences were really impressive. And here are the numbers. Messerschmitt required just 1/3 of Spitfire time to be manufactured. 1/3. Thus, there were almost twice more Messerschmitts in the sky produced over even shorter period of time. How to make a system more manufacturing friendly? And there are 3 strategies that are quite obvious. First, we have to simplify the design. We have to reduce the part count. That is completely overlapping with trimming exercise and the goal of trimming from trees. Second, we have to use cost-effective materials and cost-effective processes in production. And the third, we have to minimize the complexity of manufacturing and assembling operations. Let us develop it a little bit more. If we focus on a specific component, one element of our design, we can reduce assembling time if we, first, eliminate or minimize tangling between parts in the feather, so it is easy to pick up. Second, we can make it symmetric. Symmetry will reduce orientation time during handling. And the third, if symmetry is not possible, we can use obvious features to speed orientation. Well, for example, we can magnetize, we can put markers. We can also have a quick checklist just to check if we need the part as a separate element at all. Question 1. Does the component move with respect of other parts that has already been assembled? And question 2. Must the part be made from a different material or isolated from all other parts already assembled? If the part does not meet any of these two criteria, it is a candidate for elimination or consolidation, that means merging with other parts. They can be one. If we focus on the system as a whole, there is another DFMA checklist. 6 points. First, reduce the number of parts when possible. Remember trimming. Second, build the part in layers from the top to the down using gravity to locate parts. So it is easy, thanks to gravity, to put them one after another. Think of assembling. Third, have already assembled products stable on the workspace. For example, magnetize. Fourth, have the work lie in horizontal plane, so it is easy to move in the workspace. Equipotentiality. Fifth, use chamfers and fillets to ease mating of parts, so it is easy. It is coming to each other itself. And the last one, use snap fits, click systems, and other quick fasteners, avoiding screws, glue, welding, and so on. We need to go through several examples to illustrate the idea. Example 1. We need to get a bolt into the hole, but it requires perfect precision in alignment. The bolt must enter the threaded hole in the far side to secure it. Well, doable but hard. If we slightly modify the design by just adding a chamfer at any state where the bolt must pass through, then the alignment will happen itself. The bolt will slip it itself. In example 2, it is hard to locate the disc in the left with a specific orientation of internal holes. But if we add an external feature for orientation, look at the right picture, the part can be fed easily. Well, of course, in this case, we a little bit deviate from the round shape that is typically easy to manufacture with turning machine. But if the part is manufactured by another process, it should not be a problem at all. Example 3. This is an illustration to systematic part count reduction or trimming. The valve in the left is cinematically redundant. First, we eliminate one of 2 bumps and corresponding sliding hole. We can also delegate the function of the bump to stop the handle to the valve. We have just reduced the amount of parts 2 times. Example 4. And here goes classical idiot-proof design principle example that sounds less annoying in Japanese. Pokoyoki. Indeed, a customer or a member of trade union can mistakenly assemble one of those parts upside down. Breaking the assembling hole symmetry would not leave a chance for this mistake. What are the advantages of DFMA? First, it forces us to think about manufacturing and assembly stage during design. Second, it provides basic principles, strategies, or best practices to realize the good DFMA design. Third, it forces us to simplify the design, to trim toward ideality. And the fourth, it provides common ground for multidisciplinary design team. So basically, DFMA team consists of many experts in manufacturing, in design, in shelf life, distributors, and so on. What is challenging in DFMA? First, simplification of design for easy assembly could conflict with reliability and ease of repair performance. If a component is broken, we can replace it. It is just one component. If the whole system is just one part and it is damaged somewhere, we have to utilize the whole system. Second, almost useless for unique or small quantity of product manufacturing. So it means that the benefits of DFMA analysis are enjoyed in mass manufacturing only. And the third, the home court of DFMA is mechanical manufacturing, metal sheet production, and so on. So hardcore engineering. It has mostly developed algorithms there. It realized even an engineering design software like SolidWorks or AutoCAD. Let us wrap up. DFMA, Design for Manufacturing and Assembly. It is a design tool that tells how to reduce the manufacturing and assembling efforts. It advises on how to reduce the amount of parts, how to reduce time and complexity of manufacturing operations.